Hey, what's up, guys? So we'll keep this, uh, discussing this Turing machine versus so-called circuit model. Okay, so we will first connection. We will first say about so-called circuit family. Oh, by the way, so we already defined Turing machine and circuit. Okay, so one final technical thing is so-called circuit family. So what circuit family is that for each n input bit, right? So for example, let's say checking a n bit number which is prime or not, you might hope to write a model, right? But you hope to use circuit. Suppose you want to use a circuit to do this, right? So you will say that, oh, I hope that I have a circuit which compose on n or not gate and which is read an input and output either 0 or 1 to decide whether a number is prime or not, right? So this is circuit model. So circuit family is that you give n, there's a Cn for each gate. So for each n, you want to have a circuit to solve it, right? So you output Cnx will output that either 1 bit or n bit. Okay, so this is circuit family. For each n, there's a gate, there's a circuit, right? So these are circuit family. So for example, n is 1, there's a gate, n is 2, there's a gate, 3, 4, 5, larger circuit, larger circuit. Okay, but we need the idea called uniformity or uniformity. So what this saying is that you want to say that this circuit are computable by some Turing machine. So computable by basically you need another computer program which somehow like will output the gates. Output each gate of this circuit, and it's uniform in terms of n. So you want to make sure that each n there's an algorithm which can produce this circuit, and then you can put your input into this circuit, and this circuit will output the answer, right? So you want to have such computer program who generate a circuit. So there's a technical difficulty that if you don't allow this, then actually you can prove that there's a circuit which can solve non-computable function. Okay, so right, so you need to have you must define this circuit family to have extra condition, so that this circuit for each n is producible by another algorithm. Okay, so Cn uniform if a Turing machine algorithm generates Cn description for input, and this is technical thing. So this the description basically you can print this circuit, print the form of this circuit, and basically it says what gate, what connection, what NCW, what fan out, what swap, basically each output location. Right. So for example, there's a way to produce a circuit which generate X squared. Okay, so this is uniform is an important part, but some theory. So basically, this is theoretical issue. Okay, so once we have circuit, then we have this Turing machine circuit, then uh we can ask a time, right? We can ask some resource. So you might ask what's the memory, what's the time that to solve for this algorithm to run, right? So but in general, there for different models, right? There is maybe some different factors. So this is why we developed a more general. We have give some degree of freedom. This is why we define so-called asymptotic notation or asymptotic complexity. Okay, so what is it saying that I give you? So there are various. Maybe this is more familiar with computer science. What BO if I say Fn belongs to O of Gn, this big O basically means that Fn is dominated by Gn up to a factor. Okay, for large enough n, Fn is less equal to C times Gn. And the big omega basically defines the lower bound, say that if Fn is divided by belongs to omega G of n, basically Fn is larger than C times G of n for some C. And the big theta are basically saying that F is belong to theta of G of n. Basically, there are simultaneity is true for F belongs to big O and big omega. Or basically, you can say that F of n is bounded by some C1 Gn, bounded by some C2 Gn for large enough n. Okay, so this is just for simple exercise. I think this is familiar with computer science. If you haven't noticed, then you can check out online. Okay, so 2n belongs to big O n squared is trivial, right? Because this is linear, right? So it's bounded by quadratic. Oh, even there is a 2 here. Okay, so 2n, that's going to end 2n squared for all n need to prove it. And 2n is less than, belongs to omega n cube. Oh, this is true. This is not true. Why this is true? This is incorrect. Okay, but 7n squared plus, yeah, this is some exercise. Oh, 7n squared plus square root n times log n is belongs to theta n squared, right? Basically, its speed is exact is uh at a scale of n squared is also lower bound by n squared. You can prove it. Okay, and there is a various exercise in the textbook. So yeah, so just for you to check. Okay, maybe this one is interesting, and yeah, you can check it. All right, so for example, so now you can use this idea to just to see how many steps for this algorithm, and you only care about the asymptotic complexity. For example, sorting, right? You sort n with sort array with uh each array each cell is or each indices are some numbers, and you want to sort it. You can use compare swap. You can just say I can compare these two and then swap it. Okay, so what this algorithm say that you can from j to 1 to n minus 1 for k to j plus 1 to n, and you just compare and swap. Okay, and then you can prove that this is n squared. Okay, there are more efficient way, but this is a standard method. So for since you have this big O notation and then you can turn machine or either circuit, then you can define what time and space resource to solve a computational problem. For example, addition, fast and fact, fast and low space. Okay, I give you two numbers, bunch of numbers, right? And you want to do addition, or it will be very simple. You just add one by one. Okay, so very fast. And there are some interactive problem that we think is intractable. Basically, is factoring. I give you very two large number, you can easily produce its products. But if I give you a large composite number, it will be difficult for you to find any prime number, prime factor. So we'll study states and complexity problems and prove lower bounds. These are goal of computational complexity. I will have another PowerPoint for it. Okay, so we will ask about, let's say, inputs. We will always force input side to be n bit, right? For example, n bit number for primary this primal test. And polynomial type basically means that the resource is less than, or polynomial basically means that the resource is less than p of n for some polynomial. Okay, so polynomial basically is basically, let's say n to the k plus something, which is less n of k. So basically, which is can be represented as polynomial. And exponential basically is larger. It's not the thing larger than polynomial, but it's basically 2 to the n. There's some technical difficulty, but you can say in general exponential is 2 to the n, or basically, or I would say omega 2 to the n. Sorry, omega 2 to the n. This is the definition. Okay, so usually what people believe, or basically the consensus is that when we say tractable, basically it's polynomial. Okay. But indeed, I mean, in the actual thing, if you have an algorithm which run to the n to the 100 times, then there's no way, right? But theoretically, polynomial is good, and exponential is bad. That's it. Okay, so tractable polynomial resource, intractable basically is exponential resource. Right, so for example, add an NB number, which is On, which is theta n. You just get NB number, you just do one by one, right? So you at most get two n-bit numbers, so it's theta n. And the factoring believed to be required super polynomial operation. Yeah, so the best I know is that 2 to the n to the 1 divided by 1/3. So this is the best algorithm that we know for the classical computer for factoring. Okay, so for example, n to the 1000 is polynomial, right? And the exponential is 2 to n divided by 1000. Although that practically 2 to n divided by 1000 is faster than n to the 1000 for n to the 10 to the 8. But when n is larger enough, then finally there's a day that 2 to the n divided by 1000 is larger than n to the 1000. Okay, so people knows this polynomial care about this polynomial vector, and there's a very strong conjecture called a strong Trinitarian series. Okay, so it says that any computational model simulated by proprietary machine with polynomial overhead. So so I should say there's any physical computational model. So what this means is that any physical computer in the real universe, in our universe, can be simulated by probabilistic Turing machine with polynomial overhead. So basically that if you change one computer to another computer, you just take a polynomial overhead. So everything are polynomial. If I can use one, if there's a problem that I can use one computer to solve it using polynomial time, then I can always solve it by another, but still using polynomial time. Okay. So this is a strong conjecture. Okay. And the quantum computing will challenge this. So what history is that quantum computing try to challenge this strong territory cities because that we know, but because factoring, we believe, we believe, okay, maybe some of them don't believe, but some number theories don't believe, but in general, people believe factoring do not belongs to polynomial time in classical computer, but belongs to quantum polynomial time. Basically, you can solve it in theta n squared using so-called Shor's algorithm, which takes like 2 hours to explain the details. Module some number theory results. Okay, so structure intercities implications are restrict complexity to proprietary machine. And no polynomial solution on proprietary machine plus no efficient solution on any device, any physical device in our universe. So it's a stronger, very strong model independent theory and a very strong conjecture. And the quantum challenge, quantum computing questions strong Trinitarian cities because Shor's algorithm can solve factoring and believe intractable on classical devices. Okay, and there's are some limitation. There are challenges in complexity and how to prove is because I give you a problem then how to prove the lower bound. And then there's a quantum computing that we will discuss the detail in the next few lectures. Okay, so quantum computing is somehow like tied to open, also related to complexity because you can define a so-called quantum complexity and then you can ask exact power of quantum computer versus classical, which is a major problem in this area. Okay. Okay, so we will say, so I would like to say something about computational complexity. Uh, it's called decision problems. So there are in your computer science, right? You can ask, oh, if I give you an array, then you want to sort it. Right? But in a mathematical elegant or simplicity that we only care about decision problems. So decision problem basically the problem that I only ask you a yes or no, right? So for example, I give you a graph, which this graph is bipartite or not, right? Or I give you two two numbers. You ask, oh, whether which one whether A is larger than B, right? So I only ask you about yes or no question. And this is simplest form of computational complexity. For example, is I give a number where it's prime or not, right? So this is so this is a problem only restricted to yes or no. Okay, so formal languages is the same. I give you L. There's a language L, and you want to write an algorithm tell me that whether X belongs to L or not. And yes, it's a Turing machine. So the Turing machine can only so you restrict your Turing machine can only output 0 or 1. So time complexity basically is problem defined to be time f of n. Basically, Turing machine decide x in L in all f of time. N is the length of x. So this is a set. This is a problem that you can be solved in using Turing machine in f of n time. Simply speaking. Okay. So polynomial time is defined to be time n to the k for some k. Okay, for some k. So for example, time of n squared is a problem you can solve in by Turing machine in n squared time, all of n squared time. And yeah, time to the n to the k is a problem that you can solve by probability Turing machine using all of n to the k time. we can define a complexity P, which stands for polynomial time. So this is a famous complexity class. One definition is to be union of all the time n to the k, from 1 to infinity, 0 to infinity. So what is probability polynomial time? Basically, it's all problem that you can solve in polynomial time. Efficient solved by, or the problem which you can solve by Turing machine in n to the k time for any polynomial time. Non-trivial proof for this is primarily decision question. This is very open, I think, up to like 20 years ago. Okay, so proving problem do not belong to P is very difficult. Okay, so you want to say that, oh, this problem don't have the efficient polynomial algorithm, but how do you prove it? But there are infinite algorithms. How do you prove that this problem is very special? You don't have polynomial algorithms. For example, factoring, we don't know that, let's say you give M and L less than M, and does M as a non-trivial factor less than L. This is somehow the same as factoring problem. And this decision version, we don't know. Okay? We believe it's not in P, but we don't have the proof. I mean, it's almost impossible to prove such results. Right? Okay. Oh, and there's a interesting complexity class, which stands for use MP stands for non-deterministic polynomial time. Okay, so this is called win. Definition is the exact definitions I will give you to the next lecture. But what stands for one non-deterministic polynomial basically means that this algorithm, if the answer is yes, there's a quick witness. Okay. So for example, let's use factoring as an example. If M has a factor less than L, then there's a witness, right? Basically, it's a factor. Factor is a witness. Can be checked efficiently. You just use division, right? So to check whether a number is the factor of another number, which is trivial, you just do a check. Just do a division. Okay. So there's an efficient checkable witness. So MP stands for complexity class based on verifiable witness. So basically, if there's an answer, if X belongs to L, there's a short witness that you can check. Okay. So definition is that if X belongs to L, there exists a witness. This term N will halt in polynomial time on input X blank W. So you can say that basically it's just input X. So there's an algorithm. If the answer is yes, there's a short witness. Once you add this witness, then you can easily solve. You can easily check. Okay, so there's this X here. You can add with W and check. Oh, there's a blank here. Just to check that basically the input it has two inputs. One is X, one is witness. So once you with this addition input, then you can solve the problem. Right? And if X do not belong to L, then for all W, there's an always halts with output no. Whether this is no, this is yes. Okay. So simply speaking, if the answer is yes, there's a witness that you can. But with this add with this help with this witness, then you can solve the problem. If there's no answer is no, there's no such witness. For example, factor is witness, right? If there's a factor, then okay, you can do a division, right? If there's no factor, then no matter what division you try to do, it's always not divisible. Okay. So there's a symmetry in MP because if X belongs to L, there's a fast verification. No requirement for and no requirement for fast witness if X do not belong to L. There's a problem called co-MP, which is a reflection. I would say the complement of MP such that the language with witness when X do not belong to L, and then which is complement of MP languages, for example, not factoring. Witness for no factor less than N. So P versus MP is I would say that, or people say that this is the most important question in computer science, or the most difficult one. It should be the most difficult one. Whether a polynomial time decidable problem has non-trivial, trivial witness, right? Because polynomial time you don't have witness, right? You can directly solve it. You don't need witness. You can directly solve it by yourself. And the open question is that whether there is a problem which is in MP but not in P. Or this is asked whether P is the same as MP. Computation most believe P do not belongs to MP, no proof exists. and resolution pretty understand computational limit. And so history is that I think in the 70s that people ask whether P is equals to NP. If you solve it, you can get $1 million by Clay Mathematical Institute. But people try to prove it, but oh wait, get stuck, right? So people start to ask why proving P versus NP is hard. So you ask what's all right. So you try to prove A is hard, but okay, so you fail, and you try to prove that why proving A is hard. And I mean I don't have the time, but if you're interested to know why P versus NP is then hard, then there's a theorem called Baker-Grill and Soloway theorem, and this is hard to explain in my lecture. I can explain the detail, but we don't have enough time. But I suggest that you guys can check this Terry Stou's blog. There's a like more like intuitive way. Forget about maths, then you can know what's underlying about this question. This is like I think it's very good article that you can read. You don't need to know any maths, but you can try to but once you read this blog, then you can understand what's the merits between this theory. Okay, so yeah, just for fun, share with you guys. If you want to know more the proof, more Baker what Baker-Grill Soloway, then you can check out this computer science video that by Ryan O'Donnell professor in the CMU. Why P versus NP is difficult. This is a very interesting video. I mean, the proof is the 1 hour proof of this theorem. This is very interesting. Okay, so let's talk about Shannon's theorem. Just I think this is the last. Okay, so this is the last theorem for this video. Okay, so we know that n or not gay are universal, right? So this is what we already say. But how many of them you need to given a general function or random function, right? You pick n-bit function, right? You randomly pick whatever n-bit function. How many gates that you need to do using this elementary gate to do this? And this is an interesting question. And Shannon, which is also called the father of like communication, if I remember correctly, Shannon answered this question. So this is like close to like 100 years ago. Okay, and the answer is plasmatic. So most of the functions require exponential number of gates. Okay, and this is problem so-called in circuit complexity. So what Shannon tell you is that, oh, nice, guys. Okay. I know that most of the function is hard to compute. Fine. I need exponential gate for general function. But there's no non-explicit family of functions, which is hard. So this means that we don't have any function, we don't have the family that this is hard. But Shannon tell me that most of the functions are hard. Okay. And I mean, if you can prove that sum of particular function is circuit complexity is large, then in some case that you can prove P is different from NP. This is so-called circuit complexity. Okay, and so we will prove that we will prove Shannon's theorem. Okay. By the way, I think this is not on the textbook. So I will tell you this so-called simple counting argument. And prove most of the function have exponential circuit complexity. So before we prove it, let me just briefly say what's the proving idea. So you can count how many functions, how many n-bit Boolean functions, right? So let's say you consider this, and I can ask how many f. And the answer is simple, right? Because there are 2 to the n inputs, and each input can choose either 0 or 1, right? So there are 2 to the n functions. This is double explanation. Okay, double explanation, 2 to the 2n, right? Okay, and if I only give you polynomial number of gates, then you can shuffle this. You can shuffle you can shuffle these gates and you can compose. You can prove that if I give you like non-polynomial gates, then you can get at most one the exponential function. The number of function that you can compose is only exponential, but there's double exponential, right? So there is a discrepancy. Okay. So this is there are various versions, but one version I find is this one that n goes to infinity. The fraction of n bit function is so complexity is less than 2 to n divided by 3 and tends to go 0. So what this tell you is that uh most of the function cannot be computed by using less compute cannot be computed by circuit with gates less than 2 to n divided by 3n. So there are 2 to the n Boolean functions, right? Let's say for each input to gate is either 0 or 1, right? They're trivial. And input x or inverted input xi and the output of another gate. So there are 2 plus 2n plus t minus 1 possible gates. If there are t gates, right? Because you cannot loop itself. So you have a t minus 1, and then you have either 0 or 1 and theta or either input or is inverted. So for gate input, there is a 2 plus 2n t plus t minus 1. And then there are t gates, right? So each t gate can pick either this as an input. So you can prove that there are 2 to the t plus 2n plus 1, 2t numbers of functions. Okay. And if you pick t to be 2 to n divided by 3n, then you can prove this is only small o of 2 to the 2 to n. Small o basically is fraction is 0. So what this means is that 2 to the t divided by t plus 2n plus 1 2 to the t divided by 2 to the 2n goes to 0 if t picked to be 2n divided by 3n. So what this means is that the ratio, the fraction for this number of functions compared to whole functions goes to 0. So fraction tends to 0. Okay, so classical we have Boolean functions, right? So E theory tell you that n or not gate can compose with any Boolean function, so you are good to go, right? You have this. So but in quantum mechanics, suppose you have n qubit, right? You want to implement an arbitrary unitary, right? So remember quantum mechanics, you get this gate and you have this state, right? And you want to take a unitary, but unitary which is uncountable, right? This is like reals. There are all real entries, so these are uncountable. These are not finite guy, right? So how do you done with these finite elements? This is the quite complicated. So we will hopefully spend like 1 or 2 hours to prove it. Try to convince you there's a way to do this. Okay, so we need some elementary quantum data classical circuit. Okay, so this is the next week's lecture. So see you guys.